Hello everyone, I'm Dr. Claudia Masselli and I'm from University of Naples Federico II and I'm going to introduce my keynote speaking titled Multicaloric and Elastocaloric Based System for Cooling and Heat Pumping of Tomorrow. The topic where the work is contextualized regards the increasing worldwide energy demand for cooling that is growing up year by year. And nowadays, the most diffused technologies is vapor compression cooling that is based on fluid refrigerants. And everyone knows that the environmental impact of this technique is such critical if we consider the most focused indexes like ozone depletion potential, global warming potential, and total equivalent warming impact. A vapor compression based cooler is due of a significant contribution to in terms of TEWI because the fluids working inside are based on high value of global warming potential. As a matter of fact, in this slide are synthesized the most famous refrigerant fluids that have been succeeded over the year since the beginning of the diffusion of vapor compression technologies. In the both column, we can show the flux diagram based on the natural fluids and the synthetic fluids. Focusing on the synthetic fluids, we can observe that at the beginning of vapor compression diffusion, the most famous and utilized refrigerant were chlorofluorocarbon that were dismissed because of their significant contribution toward ozone depletion. And they were replaced by hydrochlorofluorocarbon due of lower ozone depletion potential, but still significant. And then finally, nowadays, the hydrofluorocarbon are not due of ozone depletion potential, but they present an increased global warming potential. Indeed, there are a problem in utilizing such refrigerants, and the researchers are looking for a new possibility in such terms. The new refrigerant shall present a number of requirements like being of class A in terms of toxicity and class 1 in terms of flammability, since they should be classified as not flammable refrigerants that do not propagate the fire at atmospheric pressure and at a temperature of 21 Celsius. And indeed, based on such requirements and considering the regulation that were introduced at the European level, currently is applied the EU 506/17 slash 14 regulation that schedule the hydrofluorocarbon progressive phasing down for all the application field where vapor compression is involved. Indeed, in this slide are reported the main hydrofluorocarbon currently utilized. And as we can notice, there is a strong impact in terms of global warming potential. Indeed, most of them must be replaced. Specifically, the EU regulation applies to many applications from domestic refrigerator up to centralized multi-pack systems. And in this slide, I reported the starting date where the prohibition begin in not utilized hydrofluorocarbon due of global warming potential greater than the reported and connected value. The restriction in terms of in the market are also reported in this um, slide, and we can observe an aim in 2030 of a reduction up to 20% in usage of hydrofluorocarbon in the markets. Among the main substitutes of hydrofluorocarbon, there are natural fluids like carbon dioxide or hydrocarbon that are zero low global warming potential refrigerant and low cost, but the main con is that they are not retrofitting system, and so it's not possible to employ them as drop-in. On the other side, we can observe the hydrofluoroolefin that are refrigerant derived from propane and can be replaced as directly drop-in the actual hydrofluorocarbon. And indeed, but the main con is that most of them, if considered not mixed but like pure refrigerant, are not belonging to the A1 safety class. So they present a lower moderate flammability that does not is not very prescribed for domestic usage. In this slide, we can observe the hydrofluorocarbon that are replaced by the hydrofluoroolefin. Most famous, there are YF and ZE. As we can observe, most of them belongs to A2 safety class, but their GWP is very, very low. In this slide, we can observe low-medium global warming potential mixture that are derived from the above-mentioned refrigerants, and they represent a right balance between the pure substances and the refrigerant to be substituted with. And so the global warming potential is such moderate, but not so small like the previous value. Previously shown. And indeed, for the consideration, we can observe that there is a problem in terms of TEWI, and we should analyze the TEWI instead of global warming potential for the assessment of the environmental impact of refrigerant system. And also that the retrofit problem is also a very strong theme. And in this context, okay, we can wonder why it does not change the approach. So, in this context, vapor compression cooling could be replaced by, in the future, solid-state cooling. Solid-state cooling is based on solid-state refrigerant that are caloric materials exhibiting caloric effect. Since they are solid-state materials, and so they do not contribute directly on the environmental impact. They do not provide a direct contribution, rather than vapor compression that provide both a direct and indirect contribution. So this is just the first con in utilizing them. Moreover, we can observe that a variable external field is particularized by different nature's field like magnetic, electric, mechanical, and hydrostatic pressure based. And the variation of such external field provoke a magnetocaloric, electrocaloric, elastocaloric, and barocaloric effects that manifest themselves as a temperature change under adiabatic transformation. So adiabatic temperature is a direct measure of caloric effect. As a matter of fact, in this slide I represented the four possible effects: magnetocaloric, through the application of a magnetic field, electrocaloric, elastocaloric, and barocaloric. The main pro in utilizing caloric cooling are the possible of basing on eco-friendly material that do not provide a direct contribution to global warming, the possibility of register energy efficiency 50-60% either the vapor compression, as well as less noisy devices and more compact system. So in this slide are reported the vapor compression versus caloric cooling pro and cons. As a matter of fact, the main con is that the second technology is not yet commercialized since the TRL level is still quite low. In this slide is reported the environmental impact of a cooler, and we can observe direct and indirect contribution evaluated in terms of carbon dioxide. And these are the coupled index. In this presentation, we can focus on multicaloric, but moreover also on elastocaloric. Elastocaloric is the trend main on the road studied technologies. And elastocaloric cooling is based on shape memoraloric material exhibiting elastocaloric effect. The advantages are also reduced cost for the production of cooling system and the low environmental impact. Elastocaloric effect manifest themselves through structural change represented in a two double crystalline phases like austenite and martensite, and the shape memory alloys has the main property of being able to recover their shape after the stress forcing them is removed. Here I reported the austenite to martensite phase structural phase change and the martensite austenite. When the material passes from austenite to martensite, an increment of temperature due to the elastocaloric effect is registered. When the structural change goes from martensite to austenite, a temperature decrement is observed. An adiabatic and isothermal process describe the elastocaloric effect. And two possibilities there are the main diffusers for realizing elastocaloric device from fluid to solid heat transfer or solid to solid heat transfer. The first solution is based on Brighton cycle, inverse Brighton cycle, and also carries an active regeneration that allows to recover the heat flux that otherwise would have been lost. And so for the steps applied to an elastocaloric regenerator, and here I reported loading where the elastocaloric material is forced through an external stress and it increases its temperature by elastocaloric effect. Then in the cold to hot flowing, an auxiliary fluid flows from the cold side toward the hot side. And in the third step, in the unloading, the material decrements its temperature due to elastocaloric effect, and so when in the previous factor decrements, so in the fourth phase, when the fluid flows from the hot toward cold side, the fluid cools enough to allow heat subtraction in the cold side, and so thus realizing the cooling effect. On the other side, the second choice is based on solid-solid device where there are just solid materials, not fluid, to moving from a sink and the source, and the heat transfer mechanism that regulates the heat fluxes is the conduction. The main advantage of such technique was the possibility of increase the frequency of the cycle due to the absence of a fluid. Here I reported the main refrigerant used for elastocaloric cooling. Most of them are belongs to shape memory alloys. And the one of the hot topic is the choice of optimum material for elastocaloric process. And in a slide, I reported the required that the material should present, such as low thermal hysteresis, high latent heat, and high fatigue life. Among them, the benchmark of the elastocolor technology is the nickel titanium alloy, because of the high adiabatic temperature change shown by such SMA. For developing an elastocolor device, we can start from possible configuration of an active elastocaloric regenerator. An example is reported in such slide. Also, we can focus on the type of loading that could be tension, compression, bending, or torsion. Um, Among the types of loading, the most investigated are tension versus compression. One of the cons that is shown by tension loading type is the crack propagation. So if a material accidentally breaks, the continuous tension cycle allow the propagation of the cracks, and so the total breaking of the material is faster reached rather than in compression where the crack can be confined for higher time. Also, another topic of the choice is the auxiliary fluid that shall be well designed, and also the circuits where the auxiliary fluid should flow must be optimized in terms of dimension, in terms of type of auxiliary fluid, in terms of pressure drops, in terms of operative condition like velocity and frequencies. Here I reported some of auxiliary fluid, but at room temperature, for most of the cooling field at room temperature, the main employed auxiliary fluid are air and water. Here I reported an example where in a tube containing tubes of nitinol, nickel titanium, the water can flow inside or outside the tubes. And also such technology show around a small restricted number of devices, and in this slide I reported the main numbers in this topic. Here is shown the diffusion of elastocaloric prototypes, and so we can observe that is really a challenging topic currently. Here is reported the state-of-the-art of the elastocaloric device, that most of them are distributed in Europe, but also in the United States. There are pioneers of elastocaloric technology. Here is reported one of the very first solid-to-solid elastocaloric device, like the one of Karlsruhe Institute of Technology, Germany, where a smart foil-based elastocaloric cooling device show the moving of a smart foil, and the elastocaloric effect is applied for subtracting heat from a cold sink. And here is reported the picture of this device. Then an upgrade was succeeding this first choice, and a double bridge prototype was coated rather than a single bridge one. Here is reported the comparison between the single and the double bridge in the double configuration, convex and concave. Here is reported the very first compression prototype realized at the University of Maryland in the United States, where we can see that four nitinol beds are crossed by water within hydraulic cylinders. This is a longitudinal schematic of a Maryland prototype. And here we can observe the University of Ljubljana, Slovenia, a flat plate prototype that is the very first version of a parallel plate elastocaloric prototype based on active elastocaloric regenerative refrigerant cycle. The very first CAM-based rotative elastocaloric cooling device was realized in Saarland University in Germany, where a CAM-based mechanism ensured the continuous loading and unloading of wires circularly displaced on two concentric rings crossed by hair. And here we can observe such mechanical schematic and also a picture of the experimental devices realized. But in this context, we can wonder themselves where Italy is going to fix. And as a matter of fact, the Italian contribution toward elastocaloric research is mainly supported by research from University of Naples Federico II within the development of two projects, the Sustainil realizing and the check temperature. As a matter of fact, in 2019, the University of Naples got the challenge to realize the very first Italian prototype in terms of elastocaloric cooler. And the idea was funded from the Italian Ministry of University. And so the project called Sustainable, a solution using solid state cooling and investment eco-compatible, started and is coordinated by the full professor of the research group I belong to. The project is formed by three units: University of Genova, University of Naples Federico II, and the National Research Council of Naples. The first unit occupies of realize a rotative magnetocaloric cooler that could be close to commercialization. The second unit is our unit that is going to realize Sustainil. And the third unit is the National Research Council of Naples that takes care of testing both magnetocaloric and elastocaloric material that would result most suitable for developing the device. Developing Sustainil is a really interesting challenge since this device is rotative and tension based. It mounts it consider air as it transfer fluid because so we can have a direct air conditioning application, and it mounts nitinol based wires. Here I reported the main characteristic of the Sustainil prototype that are summarized. Summarized as the main point I introduced before. And many are the parameters to be investigated and reported here, like number of wires, dimensional parameter, working parameter, and also the composition of the elastocaloric material. The investigation of all of these parameters took to the realization of the optimized project, and the experimental data of this prototype will be introduced soon. In this slide, there is reported the check temperature, another project that is coordinated by myself, and is check temperature is the acronym of controlling the heating of electronic circuits, a key approach to true elastocaloric materials in a prototype, employing them as refrigerant of inactive ultra-small refrigerator. And check temperature, different from the previous device, so a linear motion of the auxiliary fluid, and is based on bending, like forcing a field way. Air is still the heat transfer fluid, so to direct allows the electronic device cooling, and the device mount allows of the benchmark nickel titanium. Here I reported some sketch of the prototype that is targeted to refrigerator for 100 watts cooling power. And additionally, the very first, the latest project I'm going to introduce is called Multical, that is based on the realization, and also is a project coordinated by myself, and it's based on an eco-friendly heat pump based on multicaloric effect. And here, two simultaneous caloric effects are applied. Here I reported the program of the research activities that are currently being actuated in the project, that are developing the numerical model and numerical tests for designing the device. Multicaloric can be, for example, the simultaneous application of magnetocaloric and elastocaloric effect in order to increase the coefficient of performance of the device, so to experiment the same temperature jump with a lower mechanical requirement. So low work, higher coefficient of performance. So this is the future, and in the future, all the progresses will be promptly reported. Thank you for your attention, and it was a pleasure to have this speech for you.